So today we're going to be discussing moments. A moment is the tendency of a body to rotate as a result of a force. A moment is a vector, which means that it has the four attributes we've already discussed: magnitude, direction, sense, and point of application. Moments are possible in both static and dynamic systems. So when we look at a moment, a good example of a moment, or a classic example, is a diving board. So if we've got a diving board, and we've got a couple of attachment points, when a diver stands on the end and or jumps on the board, they produce a force which causes a tendency of this object to rotate around this particular pivot point right here. Now it doesn't, because it's also attached at the back here, but that's the tendency, that's its desire to do that. The magnitude of a moment is determined by the product of the force's magnitude and the perpendicular distance between the force's line of action and a point. That's written as m sub o, where o is the point that we're analyzing the moment from, equals force times d perpendicular. D perpendicular is also in some courses known as the radius, but I'll refer to it as the perpendicular distance. Because of that definition, force times perpendicular distance, there's always a point to which you have to reference a moment. So, looking at this particular image, let's do some examples. So first of all, from point O, F1's perpendicular distance to point O. Well, you'll notice that F1 passes through point O, therefore it has a 0 perpendicular distance. Now that doesn't mean that the force is 0, but that does mean the moment produced by that force would be 0. If we looked at point O, F1 applied to point O would produce no tendency to rotate. F2 to point O has a perpendicular distance of 1.5 meters. F3 to point O, since F3 goes through point O, it's not going to produce a tendency to rotate, and so that's 0. F4 to point O has a perpendicular distance. If we look at its line of action, the perpendicular distance is 1.5 meters. From point P, let's change our perspective now. The perpendicular distance of F1 to point P, well, perpendicularly, that would be measured this way, and that's 1.5 meters. F2's perpendicular distance to point P, F2 goes through point P, so its perpendicular distance is 0. F3's perpendicular distance to point P is 1 meter. Measuring perpendicularly from F3, you can see that it's 1 meter away. And F4's perpendicular distance, well, there's the line of action for F4. Point P is over here, and it's 3 meters away. I will just say it is a common mistake for students to measure in parallel. For example, I will see some students tell me that the perpendicular distance from F1 to point O is 1 meter. But that's not the perpendicular distance. That distance, you can see, is measured in a parallel fashion. For these perpendicular distances, we always have to measure perpendicularly to the force. Now, I told you a moment has a magnitude, a direction, and a sense, and a point of application. The direction of the moment is perpendicular to the plane formed by the point of application and the force. So when we look at that, that means that the moment is coming into the page or going out of the page. It's actually coming in a three-dimensional perspective. When we talk about the sense, we're talking about the type of rotation. So you can think of that as clockwise or counterclockwise. And always, from this point forward, you should be reporting 3 things with your sign convention: the positive y direction, the positive x direction, and the positive sense for moments to rotate. It is standard to indicate moment rotation as positive for counterclockwise. Technically, you can choose that, just like I could say, well, hey, I want positive x to go left, but that doesn't make a lot of sense. That's not the way everyone else does it. So I encourage you to use this sign convention with counterclockwise unless there's some compelling reason to do otherwise. The point of application is pretty simple. It's just where you measure the perpendicular distance from. So whatever point you're analyzing, that's your point of application. And the last thing I want to talk about is Verinon's theorem. A lot of times we'll have forces that are acting at angles. They'll not be right angle forces as they were earlier in these few slides. And because of that, it's really helpful to be able to figure out what that perpendicular distance is. Sometimes you don't want to find that perpendicular distance for the whole force. So instead, Verinon's theorem says that the moment produced by the force from a perspective of a certain point P here, is equivalent to the moment produced by that force's components. So if we take the x component, multiply by its perpendicular distance, and we take the y component, multiply by its perpendicular distance, and add those two moments together, that would be the same as the original force. Now in the example here, I'm going to show you how that works, but a lot of times it's easier to do this and break the force into its components than it is to try to do the trig to figure out what that total perpendicular distance is. In this particular example, I'm giving a situation where there's a pipe coming out of a wall and there's 4 forces acting on it, 50 newtons, 60 newtons, 20, and 40 respectively. And in this particular example, we're just asking to find the moment with respect to point O. Once again, this hash notation over here indicates the ground. And as stated before, I'm going to use capital English letters for my forces, lowercase Greek letters for my angles, and lowercase English letters for my distances. That's definitely not required, but it is suggested. Now I can see right here that I'm going to need a couple of additional distances. I'm going to need this distance that I'll call y here, and I'm also going to need this distance that I'll call x. And I'm going to calculate those distances in an aux comp. So the sine of theta, since sine is opposite, that would be y divided by side c. So solving that for y, and you'll find that y equals 1.5 meters. Likewise, the cosine of theta is going to equal x divided by my distance c. So x equals 2.59808 meters. You'll notice my notation here solving for m sub o. That is the moment with respect to point O, which I have labeled here on my diagram. Now, you do not have to redraw the entire diagram. It would be perfectly sufficient just to draw point O and all the forces. You don't necessarily have to draw the whole situation. The way we state this is the moment about O equals the sum of all the individual moments about point O, where I is m of f1 around point O, m of f2, so on and so forth. So therefore, the moment about point O equals f1 times d perpendicular plus f2x times d perpendicular plus f2y times d perpendicular plus f3 times d perpendicular plus f4 times d perpendicular. Now you may wonder, why am I going to break f2 into its x and y components? Well, this goes back to Verinon's theorem. I could extend f2's line of action up here and make a right triangle with f2's line of action, point O, in this horizontal line. Then I could find the perpendicular distance between that line of action and O using some trig. I don't really want to do that. So instead, I'm going to treat f2 as if it's two forces, f2x and f2y. I'll sketch them here. Here's f2x. And here's f2y. And I'm going to use those two forces and their perpendicular distance rather than using the whole force f2. Now at this point in time, it behooves you to look through the forces and determine if any of them are going to produce a zero moment. If any of the forces are zero, of course there's going to be no moment produced by them, but all these forces have a value. So next we look and see if there is a perpendicular distance between that force. So F1 does have a perpendicular distance to point O. In fact, it's A. F2, we break it into its x and y components. F2x goes through point O. Therefore, its perpendicular distance is 0, which means that that term is going to become 0. Now be careful with what you say. F2x is not 0, but the moment produced by F2x is 0. Next is F2y. It does have a perpendicular distance, which in this case is a plus b. F3 also has a perpendicular distance, and its perpendicular distance is a plus b plus x, and F4 has a perpendicular distance as well, which is y. So now we continue with our where statement. Just like before, you're still required to have a where statement. So F1 times d perpendicular equals, now is when we figure out not only what the value of the moment is, but the direction in which it rotates. So that's F1, and its perpendicular distance is a, because F1 measured perpendicular to point O is a. Now the question is it going to produce positive or negative rotation? And what I like to do is take a ruler and place it on the paper from point O to the force. I don't have a ruler here, so I'm going to use this green line instead. And if you hold the ruler or pencil at point O and you apply the force, what type of rotation do you get? In this case, if I held this line here and applied F1 down while holding it constant at point O, you can see that the type of rotation I would get is clockwise. And clockwise is defined as negative. So that means the d perpendicular times F1 equals negative F1 times A. F2x was 0, so we can ignore that. F2y times d perpendicular. Well, first we have to write the value of F2y. The value of F2y is sine theta times F2. Now we need to look at its perpendicular distance. F2y is right here, and it is a plus b away from point O. And if we do our good old ruler trick for F2y, it's going to pull the ruler down, once again producing clockwise rotation, which we have defined as negative. F3 times d perpendicular is going to be F3 times its perpendicular distance. F3 is here, measured perpendicularly to point O would be a plus b plus x. And just like before, we hold a line out here. We apply F3 at its point of application while holding the line at point O. And you can see that it would produce clockwise rotation, which is negative. And last we have F4. F4 is just F4. Its perpendicular distance to point O is y. In order to figure out which direction it's going, I'm going to hold my pencil here at point O, or my line, and I'm going to apply F4 perpendicular to that line. And F4 would cause it to rotate this way, which means that F4 is going to produce a positive moment. So plugging all of these into my original equation, I will get MO equals negative F1 times A minus sine theta times F2 times A plus B minus F3 times A plus B plus X plus F4 times Y. We can plug all our values in now. MO equals negative 453.923 Newton meters. That's a perfectly acceptable answer. However, I'm also going to write this statement so that there's no confusion, indicating its direction as clockwise. So the answer is MO equals 453.9 Newton meters clockwise. So just to sum up real quickly, when we're dealing with moments, the value of the moment is the force times the perpendicular distance to a certain point. You need to know that perpendicular distance is a perpendicular distance, not a parallel distance. Also, Varanon's theorem is what I used here with F2. Varanon's theorem says that if there's a force, we're trying to find the moment produced by that force, we can instead use the sum of moments produced by the components of that force.